So, last thing in the kinematics unit, projectile motion. There's essentially three kinds of projectiles. Okay, the simplest projectile is a falling object. Okay, I just drop something and it falls straight down. That's the simplest projectile. You wouldn't want to be underneath it, okay, if it fell a long way or was heavy, or both. Probably, especially both. All right. The next kind of simplest projectile would be one that's thrown horizontally. Okay, or let's say you drove a car off a cliff. Okay, that would be like the next simplest one because it starts out horizontal and becomes vertical, okay, as time goes by. The most complex projectile is one that is launched at an angle above the horizontal. All right, and that's probably, oddly enough, the most common type, okay, where we are, maybe trying to accurately hit a target, okay, or something like that, okay, with that said projectile. So we're going to look at kind of all three. Okay, we might only get to the first two today, a simple falling object and then the object projected horizontally. So a projectile is anything that's in unpowered flight, and that's the key here. Okay, an airplane is not a projectile. All right, it's using force, it's using energy to generate that force, and it is fighting gravity using those forces. A projectile has to be under the influence of only one force, gravity. Okay, at least for us. I mean, a projectile would obviously also be subject to air resistance and things like that in the real world, but we're going to simplify things, and we're only going to worry about, okay, gravity being its only force. Okay, so it has to be an unpowered flight. That has two dimensions, okay, except for a straight falling object. Something's just falling straight down, that's only one dimension, down. Okay, but if I have something that drives off of a cliff, okay, so here's my cliff and I drive off of it, right? Well, then there's this horizontal part, but obviously my trajectory is like this. Okay, I start out horizontal, but by the end, I'm moving both vertically and horizontally. In fact, almost immediately after, I'm moving both vertically and horizontally. The vertical part does become quite dominant, okay, by the end, because obviously gravity is causing the object to do what? Accelerate, okay? It's causing it to go faster and faster. If I drive off of a cliff in a car, I can't make the car go faster horizontally once I'm off the cliff because the wheels don't work anymore. Okay, they can spin all they want in the air. They're not going to generate any propulsion forward. Okay, gravity is simply going to accelerate me, which is why, okay, anytime you've seen in a movie a car drive off a cliff, it looks like at first it's, oh yeah, they're going really, and then it's just it looks like they're falling straight down because the downward part becomes so dominant because it's getting greater and greater while the horizontal part is remaining constant. Everybody kind of follow me on that? Okay, and this is something that if you do any target shooting, that you have to take into account. Okay? Snipers especially have to take this into account. The moment a bullet or something like that leaves the barrel of a gun, it's falling. Okay? And they have to account for that when they're aiming at their target. If their target is any significant distance away, they have to account for the amount that the bullet will fall while it's flying. Right? And that can be quite difficult if you're shooting at something that's a really long ways away. Because your bullet could fall a long way. So we'll talk about that as well, right? So the vertical dimension of any projectile motion is acceleration due to gravity. Meanwhile, the horizontal dimension is moving at a constant speed. So for the horizontal part, we're V equals D over T, right? The horizontal component of projectile motion is constant velocity. The vertical component of projectile motion is accelerated motion. So that could be any one of our acceleration formulas that we've gone over. So projectile motion is going to work in vector components and acceleration into one problem. Okay, so we've got to be able to do both. Okay, so on Earth, what goes up must come down. Okay, if I throw something up in the air, it's going to come back. If I shoot something up in the air, it's going to come back. All right, so when you see somebody, and they shoot a gun straight up in the air, if this was like the perfect physical world, there was no wind or anything else, you best get out the way. All right, because it's coming back. All right, it is coming back down. right? Now, in the real world, obviously, you shoot a bullet up into the air. When it comes back down, it actually tumbles because of the air resistance. It's basically harmless by the time it comes back down to the ground because it's not moving very fast due to all the air resistance. Okay, but if it was the perfect physical world, it would come right back down and it would hit the ground at exactly the same speed it was fired. That would be dangerous. Okay, luckily the atmosphere prevents that for us. Okay. All right, so that's the essence of a projectile. Gravity pulls the object back downward towards the Earth while it travels horizontally. Okay, that means that an object fired horizontally will have the same flight time as an object that's dropped. Mythbusters did this once. Okay, they took two bullets, one not in a gun and one in a gun, and they fired the gun and dropped the bullet at the same time. They hit the ground at the same time, not in the same place, but at the same time. Okay, because they have to fall the same distance, right? They are both affected by gravity equally. One just happens to be moving horizontally at the same time, just like the boat in the river questions. Okay, if I'm rowing across a river, I get across that river in exactly the same amount of time that I would get across a lake of the same distance. The only difference is in a river, I don't end up straight across. I end up downstream a little ways. Okay, so that's the same thing with the dropped bullet and the fired bullet. Okay? They both fall the same distance at the same rate. Seems weird, seems counterintuitive, but it's true. Okay? Everybody all right with that? Okay, so when it comes to projectile motion, we often picture things in our minds that are wrong. And that's Hollywood's fault. Okay? Because Hollywood has taught us all these strange myths about how projectiles fly. Okay, especially with the advent of CG. Okay, now they can make anything look like, like do the bullet time thing where somebody jumps up in the air and they just hover there and they kick like a whole bunch of people while floating in the air. Okay, obviously that kind of stuff just is not realistic. Okay, but with CG, you don't have to obey the laws of physics. You can make anything look real. Okay, well, back in the day before CG, okay, all those shots had to be filmed for real. Okay, they were going to jump a car over a river. They had to jump a car over a river. There was no way to fake it. Okay, they actually had to total a car. Okay, now they just drive a car up to a ramp, speed up the film, and get a computer to generate the car flying over to the other side. Okay, they don't have to worry about stunt driver, okay, insurance, all that kind of stuff. They just CG it all. Right, but it does give us a false sense of how things actually move. And I'm going to show you in the next 2 days a whole bunch of examples of horrible movie physics and some really good movie physics, because some things are done really well, some things are just stupid. Okay, and once you see them, you can't unsee them. Okay, so I'm probably going to ruin a few things for you. Okay, but that's because I need to. Okay. All right, so it also means, okay, that an object that's projected at an angle into the air vertically, okay, will return to the original height at the same speed it left. Okay, so if I throw something up in the air in the perfect world and I catch it at the same height I threw it from, it's going to be moving at exactly the same speed when it comes down because it's traveled the same distance up and down. Okay, the acceleration has been the same, both up and down. Okay, and here, VI would be some number, VF would be, how fast is it moving here at its highest point? 0. Okay, and then here it would start at 0 and go back down to the same speed. Well, after I catch it, yes, but when it first hits my hand, same speed I threw it at. Okay, so everything being the same, it has to come down at the same speed. Again, in the perfect physical world. All right. So if you are a sniper, as an example, okay, and you want to hit a very distant target, you have to, as we said before, account for many things, but mostly you have to account for drop. Right? How long is the bullet going to be in the air for? Okay, that equates to a certain distance that it's going to fall. The longer in the air, the further it's going to fall. Right? So what has to happen is the sniper will have to adjust the height of their scope. Okay? So essentially what they do is they click the scope so that it's aiming down. That way, in order to get the target in the sights, they have to lift the barrel above the target. Okay, so they're looking at the target, but the barrel is not pointed at the target. It's pointed well above it. Because once they shoot that gun, the bullet will follow a projectile arc that will hopefully encounter the target. Okay, how many people have seen the movie Saving Private Ryan? Okay, so the sniper scene in there, okay, where they're pinned down in the courtyard, Vin Diesel gets shot. Spoiler alert. Okay, it's like one of his first roles. They're all pinned down, and the sniper is talking about, you got to stay down. This guy's got talent. He's 800 yards away. Okay, so he's almost 800 meters away. And he says that's 2 clicks. He doesn't mean 2 kilometers. It's 2 clicks of his scope. So he clicks the scope twice, which adjusts the scope down. Okay, then he puts the sniper in the sights and pulls the trigger. Okay, bullet flies up over the sniper, down, back down to the sniper, okay, on a projectile arc. So he had to account for how far the bullet would drop by adjusting his scope to hit the target. Okay, if you shoot if you do archery, same thing. Okay, you don't aim directly at the bullseye in archery if it's any distance away, right? Because you have to account for the fact that the arrow is going to drop as it flies. Any projectile will do that, right? You guys follow me there? Okay, and that's true. Okay, like we have in Canada the record holder. I think I told you guys this before, right? Record holder for the longest kill shot is a Canadian sniper, 4 kilometers. Okay, bullet was in the air for like 20 seconds. Okay, it's ridiculous, or something like that. It was ridiculous of flight time. Okay, so it would have dropped an incredible amount, plus 2 different crosswinds on the way there. Okay, and the guy still hit his target. Right, it's crazy, scary. Also mostly scary, okay, that someone could do that, right? But again, all of it is projectile motion. Okay, in artillery, same thing. I mean, when I was in university, we one day decided it would be fun to take a set of bungee cords and make a slingshot out of it. So we took it up on the roof of our dorm, and we did this. So this was our dorm, and then there was the student administration building, and then there was quad. Big grassy area where people hang out when it's nice. In the wintertime, it's completely empty. And we decided, because it was a nice day, we were going to fire water balloons into quad from the roof of our dorm. Made sense at the time. Anyway, so what we started doing is firing these things over. And what we had was our friend standing here with his cell phone, which was like a brick back then, because this is like 20 years ago. So he's holding a big brick. And he was telling us where people were. And I was doing this with a bunch of engineers who could do projectile motion calculations in their head, okay? Even in that condition, okay? They were still really, really accurate, okay? So we were pegging people like crazy in the quad with these water balloons being launched from like 150 meters away, okay? Because all we needed to know was how far they had to go. And we would just change the angle or how far back we pulled the bungee cord. Okay? Mostly it was angle. We would just pull it back all the way and either shoot it higher so it would fall short, or shoot it at less of an angle so it would go a little bit further. Okay? Same thing you would have done when you were a kid with the hose, right? Like if you wanted the water to go further, you just aimed it up a little bit, right? And it would go a little bit further. Okay? So we were doing that essentially and getting people in quad, which was great fun for us. Probably not for them, but it was fun. Until 5-0 pulled up. Campus security pulled up in front, and we decided that they looked like they needed to cool off. At that point, it really ceased to be fun. That was a pretty poor decision. Splattered that water balloon right on the side of the Jeep. Kind of got in trouble. A lot of it. But anyway, makes for a good story. And it's physics related. So there you go. Okay, so what I'm going to show you here now, guys, is a video of kind of the simplest projectile motion, that of a falling object. Okay, and this is where a knowledge of physics can overcome, let's say, advertising gimmicks. Okay, this is a advertisement from like I want to say like the late 90s, early 2000s, and it was for the Lexus IS sedan. Okay, their premise was that this sports sedan was faster than gravity. Okay, they built this sports sedan. They were trying to compete with BMW and Mercedes and all that. Okay, and they were saying the car is faster than gravity. What they set up was they had one Lexus IS that was being held by a helicopter above the ground. Okay, they painted this big X on like an airport runway. Okay, and they held this car above the ground. And they had another car, the same distance horizontally that this one was vertically, okay, above the ground. This car on the ground starts, and they drop that car. And it's a race to the X. Okay, It's a race to the X. And of course, the car on the ground wins. The car on the ground will win every time, provided you make the distance right. Okay? Why is the car on the ground? Like it sounds great, right? It's faster than gravity because we envision this thing accelerating all the way to the ground. Except that in the real world, that doesn't happen. In the real world, what do all objects reach when they're falling? Well, that's their rate of acceleration, but they're only going to accelerate at 9.81 for part of the trip. And at some point, you reach your terminal velocity. Okay? That is the point where gravity and air resistance balance, and you no longer accelerate. You hit your fastest speed that you can fall at. Okay? And it's based on your shape and things like that. Like if you're a skydiver, you always see them when they're doing all their acrobatics and stuff. They spread eagle like this, right? That slows them down. If they tuck in like this, they fall a little bit faster because they have a little less air resistance. So with the falling car, it reaches its terminal velocity, and it can't fall any faster because it's falling flat. Car on the ground, however, doesn't have that problem. Okay? Car on the ground can continue to apply power and go faster than the car that's falling because it's in its most aerodynamic dimension, and it can continue to apply force. Okay? Whereas the only force acting on the car that's falling is gravity. Okay? So it sounds really cool if you don't think about it. So I'm going to show you the ad, and then I'm going to show you Mythbusters busting it. Okay? So the thing about the falling bowling ball that you don't see, and this is what, again, gives people a kind of a skewed sense of how things work, is that when you jump out of a plane, are you falling vertically? Yes, but you're also moving horizontally. So when you jump out of a plane, you're still doing this. Now, granted, by the time you hit the ground, if it's from a long way away, by the time you hit the ground, it's mostly vertical, right? Because you've slowed down due to air resistance forward and things like that. But you still are moving horizontally, okay, when you jump out of that plane. Okay, everybody kind of follow on that one? Okay, so let's look at the first kind of projectile motion here. So copy this one down. So I've got this cliff, right? And we're going to just throw something off of this cliff, right? Obviously, that something is going to go like this. Okay, it's going to have that trajectory. I'm going to throw it off the cliff at 15 meters per second. And let's say the cliff is 50 meters high. I want to calculate how far from the base of the cliff this object is going to hit the ground. Okay. So the key to any projectile motion question is to recognize first that it has two dimensions, a horizontal dimension and a vertical dimension, and that those are different. They only share one thing in common. That thing is the same thing that the river questions had in common. Okay? The across and down parts shared one thing in common, and that was time. Okay? Because once you got to the other side, you were also no longer going downstream. Okay? So they're sharing only time, but everything else is different. Okay? So here's what I know and what I want to do. I want to break this up into vertical and horizontal components separately, because I can't use vertical information in the horizontal calculations other than time. Okay? So vertically, the displacement of the object is going to be 50 meters down. What else do I know vertically? Right, I know the acceleration due to gravity. And I know one other thing. I threw this object horizontally. How fast was it going vertically at time 0? 0. Okay, because I threw it horizontally at time 0, it was not moving vertically when this whole thing began. That's the key to anything projected horizontally. If it's projected horizontally, its initial vertical velocity is 0 meters per second because it isn't falling yet. Okay? If I threw it downward, okay, then it would have an initial velocity downwards. If I threw it downwards or threw it upwards, okay, it would. But in this case, I'm throwing it horizontally, so VI is 0 meters per second. Okay, everybody okay with that setup so far? Okay, horizontally, I only know one thing, and that is that the object is going to travel at a constant velocity of 15 meters per second. I'm trying to find this, which is essentially how far it travels horizontally. Agreed? Okay, so like the boat questions then, if I'm going to find this, I need to know what? I need to know time. Okay. I need to know the time because horizontally, I know it's traveling at a constant velocity, and the only way I can get d is if I have t. Now, looking at what I have vertically speaking, I have vi, I have a, and I have d, and I'm looking, can I find t with that information? Okay, got to find a formula, an acceleration formula that has all of those things in it. Probably this one. Okay, that has all that information in it. And luckily for me, vi is 0. So really, I just have 1/2 at squared equals d. Right? So I can very easily solve for the amount of time that this thing falls for. So I've got d equals 1/2 at squared, solving for t. So I'm going to divide both sides by half of a. Okay, and that's going to leave me with t equals the square root of d over 1/2 of a. So that's negative 50 meters divided by 1/2 times negative 9.81. And that'll tell me how long it falls for. Everyone follow what I did there? Okay, just an acceleration problem right there. Okay, so it's going to fall for 3.19 seconds. The whole time it's falling, it's also traveling horizontally at 15 meters per second. Right? So just like when I cross the river in the boat, if I know how long it takes me to cross the river, I know how long I'm going downstream, and I can figure out how far I travel as a result. Okay, so we've got d equals v times t, 15 times our 3.19, okay, will give us our horizontal distance, or how far from the base of the cliff it's going to hit. All right, I only have 2 significant figures here, so we're looking at 48 meters. Okay. Now, I could also ask a question like that where I said it lands 48 meters from the base of the cliff, calculate the height of the cliff, and then you have to work backwards. Okay? And you calculate the height of the cliff by finding time with the horizontal and then using it with the vertical. All right? Guys, more often than not, with a projectile motion problem of any kind, time is the thing you're looking for, because it can be used for both components, both the vertical and the horizontal. So if you can find them both, okay, then you're set. All right, questions on how that one worked? Okay, so that's objects projected horizontally. All right. Okay, so we're going to look at a couple of other examples here, but we'll look at now what happens with something projected at an angle. Right? So if it's projected at an angle like this, let's say it's 30 degrees, okay, then it's moving upwards and it's moving horizontally. Agreed? Okay. If I throw, like, let's say I'm like playing catch, okay, throwing a football or a baseball, okay, I throw it at an angle above the horizontal, okay, let's say I threw it at 20 meters per second, okay, well, then it's traveling both horizontally as well as vertically, but it's going to follow this arc now. Okay? Any projectile follows a projectile arc. Okay? In the perfect world, the arc looks like that. In the real world, the arc is usually more like this. Okay? Why does in the real world the arc look more like that? Okay, a little bit because of spin, but if I was actually able to throw something without it spinning, I mean, really all that's causing it to slow down horizontally is air resistance. Yeah, so air resistance slows down the horizontal part, but not the vertical part. So you often see that a real projectile arc flattens at the end. Okay, but in the perfect world, they would be perfectly equal on both sides. Okay, and we're only going to deal with the perfect physical world for ourselves. All right. So that's how something would normally move. Now we're going to look at some like good movie physics, bad movie physics kind of things with this kind of projectile motion. So we want to find the height of a cliff. We need to know how high it has to be so that a person who runs off the cliff at 8 meters per second would hit the water 15 meters from the base of the cliff. All right, so as a kind of diagram of this situation, here's our cliff. Okay, the person's running off the cliff at 8 meters per second. We're looking for the height of the cliff, but we know that they're going to land 15 meters from the base. So essentially they're doing this. Right? We need to figure out how high is the cliff with that information. So first thing, any projectile motion problem, we got to break it up into its vertical and horizontal parts because they only share one thing, and that one thing is time. And it's almost always the first thing you have to find. Okay? So vertically speaking, the initial vertical velocity is 0 meters per second because the person ran horizontally off the cliff. They were not moving vertically at time 0. Okay? Their acceleration is going to be 9.81 meters per second squared down. I'm not going to make that negative because it doesn't change directions. It's all down. Okay, so I'm just going to make down positive for this one. All right. I don't have the time and I don't have the displacement. Right, but I need both of those things vertically speaking. Horizontally, though, I have the velocity. It's 8 meters per second horizontally, and I have the distance it travels, which is 15 meters. Right. From that, what can I find? Time. Yeah, I just use v equals d over t, and I can find the time. All right, so time equals d over v. So 15 over 8. It's going to give us like 1.8 or something like that. Okay, 1.875 seconds. All right, I can bring that over here because they share the time, 1.875 seconds. Now can I find d? Yeah, and I'm going to use the same formula that I used in the last question. I'm going to use d equals vi times t plus 1/2 at squared. Okay, since vi is 0, it's just 1/2 at squared. So 1/2 times 9.81 times the time squared. Okay, the cliff has to be 17 meters tall. Yeah, I would have it one significant digit because I only used 8 here instead of 8.0. So it would be 2 times 10 to the 1 meters. All right, everybody follow how that one works? Okay, so really those are the only things you're ever going to be asked to find in a projected horizontally kind of question. You're either looking for how far from the base or how high did it fall from. Really, those are the only two things you're going to look for. Once in a while, it might ask you to find how fast they ran off at. Okay, which is not, again, not all that hard. It's still, I got to find time using one or the other of horizontal or vertical, and then find the appropriate formula to use after that. Okay, they're not usually too many steps. Okay, so here's one where you have to find the speed it rolled off at. So give that one a try. Still something that's going horizontally off of essentially a cliff. It's rolling off a table, right? So it's rolling horizontally off the table. Here. So the ball is going to roll off the table. So here's our table. Okay, we are looking for how fast it rolled off. In other words, we're looking for the constant horizontal velocity at which this ball is going to travel through its entire flight. Okay, we know that the table itself is 0.85 meters. Sorry, it's 1.2 meters high. Okay, we know that it accelerates at 9.81 meters per second squared in the same direction that it falls, so I'm going to leave those both positive. And how fast was it going vertically initially? 0. Okay, from a horizontal perspective, all I know is how far it travels. right? So it's displaced 0.85 meters horizontally, and I'm trying to find v, which means I need time, right? Just like we almost always do in a projectile motion question. So again, we'll use d equals vi times t plus 1/2 at squared, except that's 0. Okay, so manipulating for t will be the square root of d over half of a. Right, so we'll have the square root of 1.2 divided by 1/2 times 9.81. All right, so we're looking at 0.49 seconds as our time there. All right, so it's fallen for about half a second. Now I can bring that over here because time is the only thing that the horizontal and vertical parts share. V equals d over t. 0.85 divided by 0.49. All right, we should be looking at about 1.7 or so, something like that. Okay, 1.72. I think we only have two significant figures, so 1.7. Right, 1.7 meters per second. Okay, is the speed it rolls off the table at. All right, are those making sense? Okay, we haven't really gotten into any that involve like finding vector components yet, okay, and we will, right? That part is coming up when we start talking about the ones that are projected at an angle. Okay. Okay. So, what I'm going to show you now is this. I don't know if any of you have seen this, but it was like this viral video a bunch of years ago called the Mega Whoosh slide. This guy made a slip and slide down a hill onto a ramp, and he shot himself through the air like an impossible distance and landed in a little tiny kiddie pool that was maybe 5 feet across. Okay. Yeah. Well, yeah, it would killed him. Okay. Yeah. So it looks really cool, and it went viral. Everyone's like, "Oh my God, he really did that!" But he did. Okay. So we'll have a look at that one, and then tomorrow we'll analyze it a little more. We've said several times that if there was no air resistance, that everything would fall at exactly the same rate. Okay, so what the Apollo astronauts did when they got to the moon is they brought a feather with them, okay, and they took a hammer and they dropped them at the same time. Okay, well on the moon there's no atmosphere, so it's a perfect vacuum. Now, obviously they don't fall at 9.81 meters per second squared because they're on the moon where there's a lot less gravity. Okay, but it's really strange. You can actually watch a feather and a hammer fall at the same rate, because on Earth you drop a feather and it does this, right? Because it catches the air. That's what feathers are supposed to do, catch the air, right? So on the moon where there's no air, it just falls. Okay, and so you can see it. Yep.